Welcome back, focused learners. Today's explainer is an absolute treat, especially if you're someone who kind of obsesses over clean architecture and just really elegant code structure. We're going to be walking through this absolutely brilliant refactoring journey that was documented in an August 18th, 2026 post by Ing. It's all about moving print content into the app monad. Now, this isn't just some quick little code tweak. We're talking about a fundamental architectural shift here, moving away from this manual, explicit data passing to a sleek, automated, implicit system using a custom app monad. So if you've ever felt the sheer pain of passing variables through literally endless layers of functions, oh man, you are absolutely going to love the solution we're looking at today. Okay, let's dive into this. The entire core conflict of today's explainer really boils down to just one huge question. Is implicit dependency injection actually better than explicit dependency injection? For the longest time in the functional programming world, there's been this super strong bias toward passing everything explicitly, right? The argument's always been, well, explicit arguments make it perfectly 100% clear what a function needs to run. But, as your code base scales up, this really well-intentioned practice can completely turn against you and create some serious structural friction. So we're going to look at exactly why that happens, and more importantly, how we can actually fix it without losing any of that safety and predictability we all expect from our code. So let's jump right into Section 1, the explicit dependency problem. Before we can really appreciate Ing's solution, we have to understand the massive friction developers hit when writing the main pipeline for a ton of different functions. It's this very specific kind of pain that just sneaks up on you as your app gets more complex. We've all been there, right? You've got this one configuration parameter. Let's say it's CLI arguments wrapped in an args type. And suddenly, you realize it needs to be accessed by some tiny function buried deep, deep down in your logic. So what do you end up doing? You have to manually pass that config parameter down through layer after layer after layer of function calls. Even if those middle functions couldn't care less about the arguments, they still have to accept them and pass them along like a bucket brigade. This explicit manual dependency injection just clutters up everything. It creates these messy, tangled pipelines where your actual business logic just completely gets buried under the sheer weight of configuration routing. It makes your function signatures incredibly brittle, and honestly, it makes refactoring a total nightmare. Which brings us to Section 2. Enter the app monad. Instead of just living with those cluttered pipelines, Ing introduces this custom app monad wrapper, and it leads to this incredible aha moment. Now, what's really interesting about this slide is the radical, almost night and day difference between the old function signature and the new one. In the old explicit approach, look at print content. It had to take a handle, then a verbosity level, and finally the pandic document, just to eventually return an I/O action. It is so incredibly noisy. But look at the new signature right below it. Print content now just takes a pandic document and returns our custom app. That's it. All of those config parameters, the handle, the verbosity, they've literally vanished from the signature entirely. We've stopped them from being needlessly passed down through all those layers. It's just so much cleaner, and it keeps the focus exactly on what the function actually does. So how does this magic actually work under the hood? Well, the new code block implements this implicit auto-dependency injection using 3 main steps. First off, we centralize access to our environment variables, like our CLI args and our handles. Second, and this is key, instead of taking these as function arguments, we just pull them directly out of our environment using the asks function. In Ing's code here, we see a call to asks to grab the verbosity, and another call to asks to get the handle. Finally, because our custom app monad is basically just a wrapper over the I/O monad, we call lift I/O to actually execute our mapped I/O action. It's this beautifully orchestrated little sequence that just perfectly wraps up all that complexity. Now, the engine running tirelessly behind the scenes of this custom app monad wrapper is a little something known as the ReaderT pattern. Simply put, this is an approach where your environment variables are passed implicitly. They're entirely hidden behind the scenes, and they just automatically get provided to every single function wrapped in the app monad. By adopting the ReaderT pattern, we achieve true implicit automated dependency injection. You completely drop the chore of manually wiring your dependencies through every single function call because the monad is basically playing plumber and handling all the pipes for you completely effortlessly. Moving on to Section 3, better than global config. Okay, so whenever developers hear phrases like hidden behind the scenes or implicitly available, I know what you're thinking. Alarm bells start ringing, right? And I actually want to pose a direct quote from Ing's source material here because it perfectly validates this exact skepticism. Quote, "Isn't this like a global config shared between numerous modules?" Unquote. It is absolutely the elephant in the room because In imperative programming, relying on a hidden global state is pretty much universally considered a massive anti-pattern. It leads to unpredictable side effects, crazy race conditions, and code that is just practically impossible to test. So the big question is, have we just reinvented a terrible global configuration pattern but disguised it as functional programming? Well, the short answer is yes. In a way, it is a global configuration and context container. But wait, there are massive, critical differences here that make it completely safe. First of all, this is a strictly type-safe environment. And even more importantly, it is entirely read-only. There is literally zero mutation happening here, which means absolutely no unwanted side effects. It's incredibly highly controlled. When you pass these environment variables to a calling function, you are giving it a very specific configuration snapshot. If you call another function with that same app monad, it gets its own perfectly isolated environment. Thanks to this architecture, we get immutability by default, we get all the awesome convenience of a global config, but with absolutely none of the danger. Let's transition to Section 4, the Python context var connection. To really cement this whole concept, let's just step outside of Haskell for a quick second. Broadening our perspective and connecting this functional architecture back to a familiar imperative language is a great way to make sure we're fully grasping the mechanics here. Aang notes that in other pet projects coded in Python, this Haskell approach feels remarkably similar to Python's content management. And this brilliantly illustrates the use of things like context var or scoped context blocks. Just think about how you handle a database session in a modern Python app, right? You don't pass that database session explicitly into every single function call. You'd go crazy. Instead, you use a scoped context block to make it implicitly available within a specific execution flow. The fundamental goal in both languages is exactly the same. Eliminate all that noise of explicit manual passing for your context-specific dependencies. So the crucial point is really clear when we stack Haskell's ReaderT pattern right alongside Python's context var. Looking at them together, we see that the injection type for both is absolutely identical. They're both implicit. They both successfully hide the explicit passing of arguments, which totally cleans up your function signatures. But the true differentiator here lies in the evaluation time. Over in Python, context vars are evaluated and enforced at runtime, but in Haskell, this entire implicit dependency injection is guaranteed at compile time. That means if there's any mismatch in your environment or you're missing a dependency, your code literally just will not compile, period. You're getting the unbelievable convenience of implicit context management, backed by the absolute ironclad safety of compile time verification. We've seen how moving to the app monad clears up those messy function signatures, how the ReaderT pattern safely automates dependency injection without falling into those nasty traps of mutable global state, and how these concepts bridge beautifully across completely different programming paradigms. The sheer power of immutability by default, combined with compile time safety, it's genuinely remarkable. It's a total game changer. So I'm going to leave you with this final thought. How will you apply isolated environments and implicit context management in your next code refactor? Are you finally going to clean up those messy pipelines? Take these patterns, play around with them, and really push the boundaries of your own architecture. Thanks for hanging out for this explainer, and until next time, keep learning and keep refactoring.